Hello, and welcome to the second of 5 lectures on symmetric computation. In this lecture, I'm going to talk a little bit about descriptive complexity. So I mentioned descriptive complexity in the first lecture as one of the motivating examples of where symmetry arises naturally, because we're looking at the complexity of high-level specifications. And I mentioned in this context Fagin's theorem and the question which arose first in database theory, Chandra and Harald's question of is there a logic for P? So I'm going to look at those in a little bit more detail this time and show how this line of research led to the study of counting logics and leading up to a notion of classifying structures by a certain kind of symmetry, which is particularly useful. So let's start by talking about descriptive complexity in general terms. So I'm assuming you're familiar to some extent with computational complexity, and descriptive complexity provides an alternative perspective in the sense that in sort of classical computational complexity, we measure the use of resources such as space, time, etc. on a machine model of computation, for example, a Turing machine. So time is the number of steps taken by a Turing machine, space might be the number of memory cells used, and so on. And we define the complexity of a language. I alluded to this already. So complexity is defined as the complexity of deciding a set of strings. That's what's input to the machine. In the context of descriptive complexity, we look at not a language as in a set of strings, but typically a class of structures, for example, a collection of graphs. So we might ask, what is the complexity of deciding whether a graph has a Hamiltonian cycle? This is a classic problem in computational complexity, but it's always formalized ultimately as a set of strings. We look directly at it as a collection of graphs. And then we measure the complexity of describing the collection in a formal logic, using resources such as variables, quantifiers, higher order operators, etc. Note, you could use a machine model here as well, and I mentioned in the first lecture relational machines as ones which work directly on structures without an encoding into strings, and you can talk about the complexity of those, but it turns out that it's an equivalent, there's nice equivalences between that and definability in logic, and I will say something about that later. In general, there's a fascinating interplay between computation and descriptive complexity, and that's what makes the subject so interesting. So let's start with Fagin's theorem, which I already mentioned in the first lecture. A collection of finite structures is definable by a sentence of existential second-order logic, if and only if it's decidable by a non-deterministic machine running in polynomial time, or in brief, existential second-order logic is the same thing as NP. And what's nice is, of course, NP is such a central concept in theoretical computer science, usually defined, like it says, as those languages decidable by a non-deterministic machine running in polynomial time. And on the left-hand side, we have something which makes no reference to languages or machines or non-determinisms or polynomials or time, but yet gives a sort of equivalent characterization. And that's what's so interesting about this. I'll give you a very brief idea of how we prove this. Okay, so there are two directions to prove. Suppose you have a formula of existential second-order logic. What does that mean? The formula consists of a sequence of quantifiers. There exists R1 up to exists Rm, where each Ri is a relation symbol, and theta, some first-order formula. Let's say if we were talking about graphs, theta would involve the edge relation as well as the relations R1 through Rm. We want to evaluate this formula on a finite structure, on a finite graph, for example. So I give you a structure A. To decide whether the formula phi is true in A, here's a sort of non-deterministic algorithm which will do it. Guess an interpretation for the relations R1 through Rm, and then evaluate the first order formula theta in this expanded structure, means the structure A together with an interpretation for R1 through Rm. Okay. And the key point here is that each of these has some fixed arity. So what does it mean to guess an interpretation? It really means, let's say, the arity of these is A1 through Am, and the size of the structure A is n. Then we have n to the A1 bits to represent an arbitrary relation R1. Each one of those bits can be 0 or 1. And we can non-deterministically branch taking either 0 or 1. And that's a polynomial number of binary branching steps. Similarly, I should really write this as a plus n to the A3. In this many steps, we can write down a sequence of bits, which is, as it were, a possible interpretation for each of these relation symbols, right? So I'm writing down a string which represents these relations. And then, once I've got this, I have got a description of the structure A expanded with new relations R1 to Rm. And I check whether this satisfies the first order formula theta. And we already know, as we saw in the first lecture, that evaluating a first order formula on a fixed structure can be done in polynomial time and even logarithmic space. So that step is deterministic polynomial time. And essentially, I have a polynomial amount of non-deterministic binary branching steps before that. So the whole computation can be carried out by a non-deterministic machine in polynomial time. Okay, let's consider the other direction. Suppose I give you a machine M and I give you a polynomial P. And I want to write down a first order sentence phi with the following property: that a structure A satisfies phi if and only if there is some ordering on the structure, so that if I then encode the structure as a string under that ordering, then that string is accepted by the machine M within P steps, where the polynomial P applied to the length of n. Okay. So I want to define such a sentence phi, and here is a rough description of that sentence. I say there's a binary relation which is in fact a linear order of A. And then you can say there are relations, I call them H, T, and S. And it's a bit tedious to write them out in detail, but think of them as coding an accepting computation of M of length P on this string. H, roughly speaking, this is going to give you tape contents. So something like at step I, tape cell J contains the symbol little a. This is, think of it as a state. At time I, the state of the machine is Q. And H, think of this as a head position. At time I, the head is pointing at step J. Now I and J here are ranging over numbers up to some polynomial P in the length of n, because the number of steps of the machine and the number of tape cells is all bounded by P of n. And you can code those as tuples. Once you have a linear order on the universe, you can code numbers as tuples of elements up to, by taking a relation of suitable arity. So it remains to say that these consistently do describe an accepting computation of M, but that can actually be then done by a simple first order formula, because you really then are describing that at each step, this is consistent with the possible transitions of M. Okay. So that's a rough outline of why, given a machine M and a polynomial P, we can write down a sentence of existential second order logic, which is true in structure A if and only if there is some coding of that structure as a string, which is accepted by M and polynomial P. So in particular, if you have a non-deterministic machine which accepts a well-defined class of structures, which means it is invariant under the tilde invariance on strings we defined before, then this sentence defines exactly the class of structures accepted by M. Okay. So that's a very rough outline of the two directions of Fagin's theorem. Now I mentioned that this leads to the question of, is there a logic for P? Okay. Which is saying, can you formulate a logic in which you can define a class of structure C if and only if C is decidable by a deterministic machine running in polynomial time? And C is decidable by a deterministic machine means, once again, that the collection of strings which encode structures in C, this collection of strings is in P. Okay, that's what it means to say that C is decidable by a deterministic machine. And as I said, formally we require the logic to be a recursively enumerable set of sentences with a translation to a pair Turing machine, deterministic Turing machine now, and a polynomial P. So this is the sense in which, in some sense, Fagin's theorem provides a logic for NP, because it gives you not only a set of sentences in which you can define exactly the classes of structures definable in NP, but it also tells you that you can translate any sentence of existential second-order logic into a pair which is a non-deterministic machine and an explicit polynomial bounding its running time. Okay, so now we know, what do we have? We have first-order logic, which is very weak. In fact, in terms of complexity, everything you can define in first-order logic is in the complexity class AC0. You can't define simple things like there's an even number of elements in the universe, there's an even number of edges in the graph is connected, all of which are polynomial time properties. If you go to second-order logic, you get something very, very rich, right? Just the existential fragment is already all of NP. If you take the full second-order logic, you have the whole polynomial hierarchy. So if we want a logic for P, it's going to be somewhere between first-order logic and second-order logic. Unless, of course, P equals NP, in which case second-order logic is a perfectly good logic for P. So the first attempt at providing an extension of first-order logic, while still remaining within polynomial time bounds, is to extend first-order logic by the power of inductive definitions. And I will give you a brief explanation of what that means. So suppose we have a first-order formula in a vocabulary sigma extended with a relation symbol R. And just to show this, I have explicitly mentioned R along with the free variables of phi, x1 through xk, or k distinguished free variables, and assume that R is of arity k. Okay. So really, I'm thinking of R as a free second-order variable inside the formula. Now, it's a free second-order variable, so that means I'm given a sigma structure A, so one which doesn't interpret R. And I think of this formula phi, right? Now, phi cannot be interpreted in A because A doesn't provide an interpretation of R. So instead, I think of phi as defining an operator on the structure in the sense that, given any interpretation for this relation R, it defines a new relation, right? So you fix an interpretation inside A for the carry relation symbol R. Now phi interpreted in this expanded structure has k free variables, so it defines a collection of k tuples, right? So in other words, it itself defines a carry relation. So phi is a map from carry relations to carry relations. That's what I mean by an operator, right? It is, so phi, this capital phi, is a map from A to the k. Sorry, that's power set of A to the k to the power set of A to the k. Okay. Okay, we have such an operator, and now I take the following sequence of relations. Start with the empty relation. I'll call that phi 0. And I write phi m plus 1 for the relation you get by applying the operator phi to phi m and taking its union with phi m. Because I'm taking the union, this guarantees that the sequence of relations is non-decreasing. And that means in any structure, certainly in any finite structure, it will reach a limit. Okay, I call that limit the inflationary fixed point of the operator phi. Okay. If A has n elements, this limit is reached after at most n to the k stages, for the simple reason that that's the total number of k tuples, and my sequence of relations is non-decreasing, right? So I must be adding at least, if I haven't reached the fixed point, I must be adding at least one tuple, and I can do that at most n to the k times before I reach a stationary point. Okay, so this leads us to our definition of fixed point logic, FP, which is first order logic, but to which I add the following formula formation rule, which is, if I have a formula over the vocabulary sigma expanded with the relation R, then I can define a new formula like this, where the variable R is bound, the second order variable R is bound. It also binds the k tuple x1 through xk of first order variables. But I apply this operator to a tuple T, which is a k tuple of terms, and so free variables other than this R and X and phi, and any free variables in T remain free in this new formula. I should read this formula, this is informally defining its semantics, as saying the tuple of elements T is in the inflationary fixed point of the operator defined by phi. Okay. Now, I wrote IFP here. That's for inflationary fixed point, but I just call the logic fixed point logic. There is a sort of more classical definition of fixed point logic where instead of inflationary fixed points, you take least fixed points. But for that the formula phi has to define a monotone operator, not an arbitrary operator. All right. So roughly speaking, going back, in least fixed points, you don't have the union, but the operator phi has to be monotone, which still guarantees that the sequence is non-decreasing. And to guarantee monotonicity, we syntactically restrict ourselves to positive formulas. So that makes this definition a little bit more complicated because there's an additional syntactic restriction on phi. To avoid that, we just take inflationary fixed point, and it is proved, it's a non-trivial proof, that actually in terms of expressive power, the two logics are the same. This was proved in the context of finite structures by Gurevich and Schiller back in the 1980s, and Stefan Kreutzer showed that it extends to infinite structures as well, this equivalence. Okay, so here is a simple, this is the classic example of a fixed point formula, and it shows you how this takes you beyond the expressive power of first order logic. So here is a first order formula phi, right? And I think of the binary relation symbol T and the two first order variables x and y as free variables. So I'm going to interpret this whole thing, right? So T and x and y are bound by this fixed point operator. So I'm going to interpret this in structures which have a binary relation E. And the point is that this whole thing, this whole formula defines the transitive closure. I should say the reflexive and transitive closure of the relation E. So let's look at why that's the case. You look at this formula inside phi, and T is a free relation variable. So what is, if you look at the operator it defines, what is stage 0? Well, stage 0 is always the empty relation. What is phi 1? Well, you substitute the empty relation for T. And what do you get over here? Well, this tzy is always false because t is empty. But this disjunction is true whenever x equals y. So this will give you all the pairs x, y, such that x equals y, right? Phi 2, what's phi 2? Well, now for t, you substitute phi 1. So this is all the pairs where z and y are equal. And this gives you what you had before. Actually, because I've got this disjunction, you get x equals y, or those pairs x, y, says that there is a z, y is equal to z, and there is an edge from x to z. So it'll give you phi 1 along with all the pairs x, y, such that there's an edge from x to y. In other words, all the paths of length at most 1. And similarly, you will see that stage m plus 1 will give you all pairs x, y, such that there's a path of length at most m from x to y. So in short, this will reach a fixed point when precisely this relation is the reflexive transitive closure. Okay. Now this I apply to two new free variables u and v to give a whole formula with two free variables u and v, and this formula defines the binary relation, which is exactly IFP, exactly the reflexive and transitive closure of E. This shows us that the expressive power of fixed point logic properly extends that of first order logic. But it's still the case that anything you can define in fixed point logic is still in polynomial time, right? Anything you can define in first order logic is in polynomial time. And the same is true for fixed point logic. And for this, all you need to check is what happens. So inductively, we're evaluating a formula of fixed point logic. We know how to deal with all the ordinary first order cases, the Boolean connectives, the existential and universal quantifiers, and so on. What do you do with a fixed point? Well, you essentially just iterate an operator starting with the empty relation, and you iterate it. And because whenever you have a fixed point of an induction of variety k, you reach the fixed point in at most n to the k steps. K is a constant which depends only on the formula. The whole evaluation is still within polynomial time. In fact, Immerman and Vardi independently proved this beautiful theorem, which says that if you restrict yourself to structures which come equipped with a linear order, then in fixed point logic you can express exactly the properties that are in P. I mean, this was originally formulated in terms of least fixed point logic, but as I said, inflationary fixed point logic, which was in some sense introduced later and is rather more robust, is equivalent in expressive power. So, briefly, why is this true? I've already given you one direction. Anything you can write down in fixed point logic, you can evaluate in polynomial time. You just do it inductively on the structure of the formula, and everything works. In the other direction, remember from Fagin's theorem, we said that if you have a machine M, non-deterministic machine M, and a polynomial P, you can write down an existential second order formula which defines exactly the structures which can be coded into a string accepted by the machine. And the formula of existential second order logic looked something like this. Okay. Now the point is that if M happens to be a deterministic machine, then the computation of M can actually be defined inductively. You don't have to say there exists a computation. You can actually deterministically, inductively construct that computation, HT and S. What you can't do inductively is define a linear order. And that's why in the statement of the theorem, you assume that the linear order is given, so you don't have to say there is a linear order. You just have to say there exists an accepting computation, but the accepting computation of a deterministic machine is unique and can be defined inductively on the ordered structure itself. So this is the key idea. The order cannot be built up inductively. can we, in some deterministic way, define a canonical string representation for a structure in polynomial time? We don't know. Okay. If we could, in particular, we could solve graph isomorphism in P, but this is in some sense a stronger assumption. So if you could construct a canonical string representation of a structure in polynomial time, it would follow there's a logic for P in the sense that Chandra and Harrell and Gurevich asked the question. On the other hand, if you could show that there is no way to construct a canonical string representation, it would separate P from NP. So this is a hard question. Another way of thinking of this is any polynomial time decidable class of structures can be expressed by a sentence of fixed point logic which uses a linear order as a symbol, but whose interpretation in a structure is invariant under the choice of order. Okay. That is, if I give you a structure without an order, like a graph, and I choose two different orders on it, then either both of those expanded structures will satisfy the sentence or neither will. So that's what we call an invariant sentence, and the collection of invariant sentences is in some sense a logic for P, but not in the sense we want, because it's an undecidable property of a sentence whether it is invariant in this way, in fact. So it doesn't give you even a recursively enumerable set of sentences. And if I don't allow the order, if I just take fixed point logic by itself, then that is just too weak to express all polynomial time properties. Okay, we'll be back after a short break.